Bismillahirrahmanirrahim, lecture number 2A, property of the pure substance. In our last lecture, we did some basics of thermodynamics. Today lecture, we will be doing some more basics, and today we'll be talking about the property of the pure substance. So what exactly is a pure substance? So a pure substance is a material with a homogeneous and invariable composition. A substance that has got a fixed chemical composition throughout is called a pure substance. Water, helium, carbon dioxide, nitrogen, and so on and so forth, they are called as the pure substance. Uh, Make sure like we say like it is a fixed chemical composition. The physical properties physical composition can be changed. Uh, to explain it, like the pure substance have got multiple phases. It can exist in ice, it can exist in a gas, vapor we call it. An air steam mixture, if you're talking about the air and we are talking about the steam itself, it's a mixture and we do not call it as a pure substance. um, air, air being composed of nitrogen and oxygen and other inert gases like other gases are not formally called as a pure substance, but experience show that it is a little bit more or less regarded as a pure substance. For example, if you are saying like nitrogen, if you check the composition of nitrogen, it will be roughly around 78%, and if you check the composition of oxygen, it will be around 24% most of the places. So if it is that composition, definitely air would be regarded as a pure substance. Now, the pure substance itself have got the different phases of it. Um, we have got the three principal phases: solid phase, liquid phase, and gaseous phase. Uh, the substance definitely can coexist. Have got the several other phases within the principal phases as well. For example, the solid carbon exists in diamond. It can exist in graphite. Iron has got three other solid phases. It also can coexist in one substance can coexist in different phases as well. For example, if you put an ice in a water, so that means like the water is now having two different phases. One is a solid phase, which is ice, and one is a liquid phase. Uh, but you can imagine like these two different phases are separated by a boundary, and that boundary is called as a phase boundary, distinct boundary. You can check it like that. That would be a boundary, and that two phases are separated by a boundary. Even if you can imagine like if you mix oil in a water, so we have got two liquid phases of a different substance, so that means like two different substance can exist in a one phase as well. So yes, we can talk about different phases, but that's what I mean to say like we have got different phases of the substance. It can coexist, it can be separated by by a distinct boundary as well. um, In general, solid has a strongest molecular bond. Solid are closely packed three-dimensional crystal. Their molecules do not move relative to each other, and they have got different intermolecular bond strength. We do not regard it as a perfect molecular strength, like for the strongest molecular strength, because if you want to deform or if you want to change the shape of the solid, you can actually change it with different by applying different forces. So that means like if you can apply, you can change the shape of the solid. So definitely you are not talking about the strongest or the ultimate strong bond strength. Liquid molecule spacing is comparable to solid, but their molecule can float about in a group. There is a molecular order within a group, weakest molecular bond strength. Yes, liquid has got the weakest, and if you want to, if you just push them, or if you give them a little bit energy, the bond strength will break, and definitely the phase transformation will be there. Molecule in a gas phase are apart, far apart. They do not have got the order structure. The molecule move randomly and collide with each other because they have got so much of energy with them. So they move around randomly, they collide with each other. Their molecular are highest energy level. They must be release and they must release large amount of energy to condense or freeze. Like if you want to condense them or to freeze them, obviously you need to take the energy out of the molecule. So that's why the molecule will come closer and it will actually form in a liquid, or it will change into a liquid. For a gaseous phase, they do not have got any molecular bond strength. And if they have got any molecular bond strength, so obviously we are talking about not an ideal gases. We would be talking about some other forces that imagine like van der Waals forces or Radley Kong forces, uh, blah blah blah. You can talk about different non-ideal equation and non-ideal behavior of the gas. Um, Sorry, not Radley Kong forces, but van der Waals forces by, and Radley Kong is the extension of the van der Waals. Let's have an experiment, and let's have an experiment of solid liquid phase equilibrium. Um, Often different phases, I just say like often different phases of pure substance can exist in equilibrium with one another. Let's have an experiment, let's have a thought experiment in which we start boiling our water in an open container. Let me say like I've got an open container, and let me put some water inside the container, and let me heat it up, and let me put heat on it, so I supply some Q in it. So if I'm saying like there is a heat supply to it. So what would happen like for after a while, the heat will be absorbed by the water and it will start evaporate. But once it's evaporate, it is mixing with the air particle which is above the surface of the water. So now if it is mixing with the air particle, it is definitely not now the pure substance, and our experiment with the pure substance will definitely not continue. So now it is not a pure water, cannot be regarded as a pure substance. So what we will do? First thing first, we will put some lid on it, or in other words, we will put some piston on it. Let it that piston be free to move, uh, but definitely it should be tightly sealed, so there will be no water escape or there will be no steam escape from it. As it is free to move, so that means like on the other side of the piston there is an atmospheric pressure, so that means like the piston would be moving under the atmospheric pressure. For a start, we would be considering the 1 atm, which is 100 kPa, 0.1 megapascal, and is power for 5 pascal or 1 bar to be very precise. um, and now let's start the experiment. Now again I'm saying like the piston is free to move, which means like it is under the constant pressure, and also there is and also we are considering that there is no mass of the piston, so the piston is massless. So that means like there will be only and only forces that the water would come up would be the atmospheric pressure, which would be exerted from the top. Now let's start, and let's start the experiment with the with 20 degrees centigrade. Let's start heating up. So when you start heating up, what would normally happen? The molecule would start taking energy, and then that energy would be, once the lower layer of the molecule absorb enough energy, it will be actually transferred to the upper layer, and so on and so forth. So in the start, what I'm saying like there would be actually energy transfer from the heat source towards the molecule of the water. um, but there would be a little bit slightly increase of the volume. As heat is added, there would be definitely increase in the temperature, but there would be a very slightly increase in a volume. So what would happen like if I'm drawing the TB diagram, which is temperature volume diagram, there would be increase in a temperature, but definitely there would be slight increase in a volume. Make sure the water is still in a liquid phase. Now, till when it will absorb the energy? So let me come back to this figure again. So what would happen? There would be actually energy absorbed by the layer, then there would be another energy absorbed by the layer, and so on and so forth, until the whole of the molecule have got enough energy absorbed now. Or in other words, we would say like the water is now saturated. The water is saturated in terms of energy. Now if you want to supply more of the energy in terms of heat, so there would be no temperature rise. So if there is no temperature rise, what would happen? Like the molecule which is at the top of the layer, or which is the top layer of the water, it will try to get the energy and will try to escape, and it will try to change its phase. So what happened, like we did say, like let's say if I'm saying like I did supply energy from A to B, but once it reach B, it gets saturated. Now once it's saturated, the temperature would remain constant, and the whole of the energy which you are supplying to the molecules, that would be only and only used to change the phase of the substance, or change the phase of the water. So what would happen, like from A to B, if we have got a liquid over here, so now from B to C, there would be a liquid particles somewhere over here. There would be liquid particle, and that liquid particle would start absorbing heat, and it will be converted into vapor. So from B to C, we would be saying like there will be a phase transformation from liquid to gas. But what I'm saying, like inside this B to C, or in between this B to C, there is a two phases mixture. That means like we have got a liquid as well, and we have got a gas as well. So the temperature would remain constant. The process would be again now isothermal as well. Make sure if we started the experiment with isobaric, which we mean like we are having a constant pressure as well. So now the process will be isothermal as well as isobaric. The volume will still continue to increase. We notice that the phase is present in it, as we say like there will be actually a liquid in here, and there would be actually vapor in there, and they would be separated by a distinct phase boundary, as we said a little bit earlier. The density of the fluid would be greater than the density of the gases, while the volume of a gas would be greater than the volume of a liquid. Uh, Now, what is actually this temperature? I say like this is a saturated. When it becomes saturated, this temperature normally you normally would call it as a boiling temperature, but we would call from now on we will call it as a saturated temperature. So that means like we are having a phase transformation in a saturated temperature, and for the water, that saturated temperature is 99. For a pure water, the saturated temperature is 99.62 at a certain volume. Now all the vapor, and there would be no liquid, but make sure we still have got the pressure which is 100 kPa, and we still have got the temperature which is 99.62, and we would call it as a saturated vapor state. That means like the point C would we call it as a saturated vapor phase. Now as all of the gases are desaturated, and the whole all if I'm saying like the whole of the phase is gas, and it is actually in a saturated. Now if you still continue supplying heat to the system, what would happen, like the molecule which was saturated, or the gas molecule which was saturated enough to have the enough energy, will now try to absorb more energy. It will try to get more apart, and now getting more apart would mean like the volume would increase, but also now the temperature would increase. So that means like this process will be from C to D, although sorry, it is all gas, but now we would call it as a superheated gas. So from A to B we have got a saturated liquid, getting from not sorry from A to B, not from A to B. From A, we are starting as a liquid. At B, we have got a saturated liquid. From B to C, we are starting from a saturated liquid, but there is a phase transformation. When we reach towards C, all the all the liquid is converted to gas, and we call it as a, now point C is called as the saturated vapor point. Now from C to D, actually we are supplying more energy to it, and once we are supplying more energy to it, the gases are now getting superheated or super saturated. So we have got from A to B, we have got liquid. From B to C, we have got liquid and gas mixture. And from C to D, we have got gas now. While point B is saturated liquid and point C is saturated vapor. Now, if we add more heat, as we said, both the temperature and volume will rise. With the pressure remain constant, we did say like we would try or we would perform this experiment in a constant pressure process. The water remain in all vapor state. So now we have got all gas. This is called as a boil water. This process is sketched on a temperature and specific volume diagram. And let's move forward to this one now. So now we have got the saturation temperature, or saturation temperature we call it as a, if previously we were calling it as a boiling point. Um, Now let's move to another pressure. Uh, let's start with the with an example like if you are having a low pressure is somewhere like above sea level to the mountainous side actually. So what in that case, what happened like the boiling point reach a little bit earlier. So that means like when you have got a low pressure, the saturation temperature become lower, but the problem would be the boiling time, or if I'm saying like the phase transformation from the liquid to gas, it is actually taking time, or it is actually a little bit extended. So what happened, or what I mean to say like during a low pressure, we would get a boiling point very early, but we would not get the VG a little bit early. So that means like there would be a little bit more time so that the volume VF is converted to volume VG. And obviously the thing would be the same. Now let's increase the pressure like normally in a pressure cooker. In a normal pressure cooker, the boiling point reach a little bit later, if I'm saying a little bit late, but the cooking time, if I'm saying like, or the evaporation time is quite quick. So that means like if you are increasing the pressure, the boiling will be a little bit earlier and the saturation temperature would be a little bit late. So it will be something like this. And if you still increase a little bit more, it will be more like this, and so on and so forth, until you reach a point when you, sorry for that, until it reach a point when you apply something, if I'm saying like apply when you supply heat to it, it will be directly, the liquid will be directly converted into gas. So it will be something like this. That means like, let me a bit rough example to you. If you have a very hot plate, and if you just drop a water droplet on it, so the droplet will just eventually, if I say like the droplet will be very quickly converted into liquid. So you will definitely not find a phase or two phases mixture somewhere. So that means like if the temperature is high, the pressure is high, the liquid will be directly converted to gas. Now if I join the saturated line, saturated liquid line, and saturated vapor line, so it will be, graph will be something like this. Now we have got different, you can check, we have got different lines in it. uh, these lines or these points. Let me put the points first. These points which I've drawn, which I've combined, the line which actually I've drawn is actually called as the saturated liquid line. By joining these points, saturated vapor points, the line is called as saturated vapor line. Inside the saturated liquid line and saturated vapor line, we have got a two-phase mixture. From this side of the saturated, on the left hand side of the saturated liquid line, we have got the liquid. We have got the phase which is all liquid. On the right hand side of the saturated vapor line, we have got the phase which is all gases. So that, and obviously on this point we have got all liquid and it is saturated. On this point we have got all vapor and it is saturated. The point at which it is converged, or the extreme point, this is called as the critical point. That for the water, the critical point is at the pressure of 22.089 and the temperature, critical temperature is 374.14. On a critical point, the volume Vf is equal to Vg, which is actually, we call it as a critical volume, and which is equal to this much for a water. So this is what we call it as a TV diagram of a liquid, of a phase diagram of a water on a TV. Now, if I draw, if I draw it on a PT diagram, so that means like the pressure and volume diagram would be something differently. If I'm saying like not linearly moving, a little bit exponentially, but it will be something like this on a PT diagram. Or in other words, if I'm saying like, let me put it here. If I'm increasing the pressure, that is my pressure 1 atm. This was a pressure less than 1 atm. This was a pressure greater than 1 atm and greater, and so on and so forth. So if I'm increasing the pressure, the saturation temperature increases. So that means like the saturation temperature is increasing as the saturation pressure is increasing as well. So the graph of the PT would be somewhere like increasing the pressure would increase the temperature, increasing the saturation pressure would increase the saturation temperature. Now what does this graph actually say? Now that means like if I'm saying like I've got the 1 atm somewhere for the water, so the temperature corresponding to that would be somewhere around 99.62. Now if I'm decreasing the pressure from 1 atm, the temperature saturation will be decreased. Now if I'm increasing the temperature, so that means like the temperature saturation will also increase. So this graph is more or less what we call it as the phase diagram, or the PT phase diagram of water. Now if I'm saying like what is this point actually, if you can imagine like this, these are our boiling point. And if I'm saying again, now if I'm having a 1 atm temperature, 1 atm pressure, and if I'm less than 99.62, let's say if I'm less than 99.62 but I have got a pressure of 1 atm, so I am still inside the liquid region. Now on a once I reach 1 atm and 99.62, I have reached towards the saturation point. Now if the same pressure continue 1 atm and I increase the temperature, and let me say like if I increase the temperature at 102 degrees centigrade, so that means like I would be in a gaseous phase. So that means like this PT diagram is telling you the distinction between the liquid and gas phases, and it is separated by a line, and that line is, we call it as a saturation line, you call it as a boiling line, you can call it as a liquid and gas equilibrium line, and that you can differently name it depending on what you are saying. If you can call it as a condensation line as well, if you are moving from gas to liquid. So this line is what we normally would call it as a liquid gas equilibrium line. uh, let's say let's check some of the nomenclature that we would be adopt. We would be having a saturated liquid. One, if we are talking about the saturated liquid, the material is at T saturation, the temperature is T saturation, this one, it is saturated liquid, and the phase is all liquid. If the phase is all vapor and it is still saturated, we would be calling it a saturated vapor. The material is still at the temperature desaturation, but it is all vapor. So we will call it as a saturated vapor. If it is less than saturated, we are inside the liquid region, but that liquid region is called as the subcooled liquid region or a compressed liquid region, as the temperature is yet not saturated. So we will be calling it as subcooled, and the pressure is yet not saturated, we will be calling as a compressed region. So in that region, let me rub it for you for so that we can have a little. So from that region, this is our T saturation. If my temperature is less than T saturation, that means like I'm in a compressed region and I'm in a subcooled region. If my temperature is greater than T saturation, I'm in a superheated region, or I'm in a total gas, but it is a superheated region. But if my temperature is equal to T saturation, I'm inside the vapor dome. Oh, sorry, I did not call it as a vapor dome, but normally this thing is called as a vapor dome. So I'm inside the vapor dome, and we call it as a two phases mixture. So that means like superheated region, temperature is greater than saturation. For a two phases mixture, the liquid and the vapor is coexisting. It is actually in a mixture region, and the temperature is saturated. Rewind it again. Sorry, saturated, when we have got the temperature saturated liquid, when the temperature is desaturation and it is the phase is all liquid, we will call it as a saturated vapor when the temperature is desaturation, but it is all vapor. We will be calling it as a compressed or subcooled when the temperature is less than desaturation. We will be calling it as a superheated vapor when the temperature is greater than desaturation. And obviously, we will be calling it as two-phase mixture if the liquid and vapor is coexisting and the temperature is saturation temperature. Now, moving towards the another concept.